Recording is rolling. It is Thursday, September 19th. You guys were just picking up your linear motion quizzes from your folders back there. All right, so corrections opportunity. I threw this on the board a few days back. Let's go over this again. So if you missed some quiz questions and you want partial credit back, here's how you can do that. You can take a separate piece of paper and write out the correct solutions for all the puzzles that you missed. There are three main types of questions I ask. I'll usually ask some graph questions. If you missed a graph question, I will have drawn in my correction ink, how to draw it correctly. So just go ahead and draw that. Draw the axes, variables, units, draw the correct curve shape for whatever story you have. Right? If I ask you guys a conceptual question that's kind of a sentence answer that doesn't really, kind of hard to make an equation with that, just go ahead and write out the sentence. There might be a couple of those. Right? And then a lot of the questions I ask are these right here. They're algebra based. There's some kind of equation you can set up and you can solve the equation. And the questions I ask on the quiz are either something we've done in class or something really similar. And I will have circled the correct answer on your quiz. So I think you should be able to figure this out. Now, if you're really, really stuck and you just really absolutely cannot figure it out, then you can ask me and I'll show you how to set up the equation and solve it. But I think you should be pretty good. So there you go. There's a corrections opportunity. If you want partial credit back, just staple your quiz to your corrections, turn that in the grade tray, and I'll give you a few points back. Okay. Textbook puzzles. I want to mention that here. I'm doing a video I might use for multiple classes. So I've got three different types of classes. Let me just go ahead and show the textbook puzzles. For my honor students, I have chapter 4 forces in 1 dimension and chapter 5 forces in 2 dimensions. Notice I've circled certain questions. We're going to mostly focus on those. Paced out pretty well in the past. For my AP students, I have chapter 4, and so these are forces, dynamics questions. Again, I've circled a few I want to more focus on. For my conceptual students, chapters 4 through 6, there's one chapter for each law of motion. I have a bunch of conceptual type questions. Now, so depending on what class you're in, you got one of those papers. Now, I do not have a due date on any of this stuff yet because I want to solve a bunch of these with you guys in class, show you guys how to solve them and solve a bunch, right? So no due date yet, but I'll eventually pick up that page from you guys, right? And let's see all your work and get to the correct answers for those, right? Right. Here's last couple things today. I have a mystery cup puzzle for you guys we're about to do, and right after that, we're gonna we'll do some posters, some of the posters, and then we'll go into free body diagrams. I have a PowerPoint, and that's gonna finish out today. Okay, are you guys ready? All right, so let's look at this mystery cup. Mystery cup. Oh, you might see a little smudge mark here because this is gonna involve some water. We're about to have some water going on here. Right, so, oh, look at this cup. This looks like just a normal cup. I would drink from that cup. You guys think you would drink from that cup? It's a normal cup. Right? Oh, hold on. What's this? There's a hole in the bottom. A hole in the bottom of the cup. And flip this upside down. Oh, hey, there's another straw hole right here. You guys see like a straw poking through? Huh. So there's some kind of straw hole going on. I wonder if this would even hold water. By the way, history of this cup, this goes back a few thousand years to ancient Greece. Let me try to fill this up with water off screen. All right. Oh, good. It's gonna work. This is one of those puzzles that half the time it works all the time. So there you go. So I filled this up halfway with water. You guys see, it's filled halfway with water, and the water's staying in the cup. Hey, I saw some kind of straw holes in it, but it looks like it's still okay. And this could still work as a cup, right? And so suppose it was thousands of years ago. Let's call it ancient Greece. And you go to a dinner party, and you get your cup filled halfway with water, and you're unsatisfied with that. You're like, I want more water. Give me more water. I'm greedy. Put more water in my greedy cup. Say, what I seriously. So the host comes over, pours more water in. I'll do this off screen here. We're gonna fill up to the brim, and then here. If you're watching this video at home, let me do a camera adjustment here. Let's take a look over here. Oh no! All the water's pouring out the bottom. Make it stop! Make it stop! I cannot do. I'm getting all wet. And all this water's just pouring out the bottom. And so you guys saw what just happened. Is I filled the cup halfway with water. The water stayed in the cup. I filled it to the brim, and now the water's pouring out. But wait, there's still one more part of the story. Okay, there it is. Okay, so you guys see it was done draining, right? Okay, so if you're watching this video at home, right, watch. You guys can see class here. All the water drained out. It all drained out. Well, except for there's a little dregs, but that don't really count so much. Right? So right here, let's get a diagram going. I'll show you guys on a diagram what just happened, right, to recap this. Right, so here's a cup. As I looked at the top, I saw a straw hole in the bottom there. I looked down below, I saw a straw hole there, right? Now, there's some kind of straw going on in the middle. And the question is, can you figure out what's going on with the straw? Here's what happened when I put in some water. I filled it halfway, and the water stayed in the cup. It worked perfectly fine. right? In fact, if you weren't greedy back 2,000 years ago, you just drink that and you'd be fine, right? But if you're greedy, give me more. I certainly. If I fill it up to the brim, now the water starts pouring at the bottom. You know what? But here's what I catch. The water didn't just go back to the previous level. It was fine before. No, the entire cup drains. Ooh, right? Now, a lot of times I'll have one or two students that can figure this out pretty fast. Right? So yeah, if you can, just hang tight because I want to give all your classmates a chance. I want to revisit this on a different day. So give everybody an opportunity. You can think about this tonight. You're going to sleep. How did that cup work? How did the greedy cup work? What? How did it fill it halfway? It stayed in. I fill it to the brim and the entire thing drains. What's going on inside? I did something with that straw. There's something I did with the straw inside that made exactly that happen. You guys get the premise? You guys good? All right. So yeah, I'll give you guys a night to think about that, and we'll probably revisit that tomorrow. I know we've got a pep rally too, so careful about that. All right. So in the future, we'll go back and revisit the solution to that. All right. You guys ready for new stuff? Actually, I'm going to rearrange this a little bit. I'm going to let me bring Newton's law to the front. I know we did some of these we're about to do today. We did briefly look at yesterday, but they're worth seeing again. Right. And then there's going to be some new posters here. Let's do some posters. Right. Let's hit Newton's laws real fast. I think I did a couple of these with you guys yesterday. So first law of motion, Newton's first law of motion. An object at rest will remain at rest. You guys see a bunch of stuff just sitting at rest on the tabletops here? Is it spontaneously jumping off the tabletops? No, everything's just sitting at rest, right? And an object in motion will maintain its velocity. Now, you guys know what velocity is. It has two parts to it. It's speed, but also direction of motion, right? So anything in motion wants to keep moving in a straight line at constant speed, right? Unless or until there is some external, I should say external net force. I need to go back and add the word net here. External net force acting on that object. That's also called the law of inertia, right? So if anything is at rest, there must be zero external net force acting on it. But also, if anything is constant velocity, let's say in a straight line at constant speed, that's also true that there's zero external net force. One of my classic examples for Newton's first law of motion is Voyager spacecraft. Guys, Voyager spacecraft, it was launched back in the 1970s, and it's still going away from Earth to this day. It's been traveling for decades. It's traveling away from us really, really fast. It's about the edge of the solar system. It's just going and going and going. Guys, how much fuel does this need to keep going? Zero, no fuel. It's just coasting because there's no significant gravitational forces nearby. There's no significant net force. It's just going because of inertia. Okay. Right. A lot of times, if you think about the how the laws of the universe work in deep space, you can strip it down to the fundamentally how things work, and that's an example there. Right. There's also Newton's second law of motion. It says where acceleration comes from. You guys know what acceleration is. Acceleration is a rate change in velocity. Or at least that's how we've been thinking about it last 3 weeks. Right. Now we're saying how you get acceleration. You get it from some kind of net force. So the acceleration is directly proportional to the net force. That means if you triple the net force, you'll triple the acceleration. Right? Triple the number of newtons, you'll triple the number of meters per second squared. Right? But the acceleration is also inversely proportional to the mass of the object itself. So if you triple the mass, you get 1/3 of the acceleration. Ooh, let me show you guys that right here. What if you have a small object versus a large object? What if I put the exact same force on both of these objects? How will they accelerate? Let's see. Force on this guy. Force on this guy. You guys see? Here, I put the same force on two different objects. A tiny mass accelerated a lot. A large mass accelerated very, very little. Ooh, and that's an inverse relationship there. Okay. Right. A lot of times this is written as F equals ma, so you might see it that way too. I like the fraction for myself. I think it explains a little bit better cause and effect. Okay, you guys good with that? All right, let's look at Newton's third law. This is the equal and opposite rule. For every active force by object A on object B, there is a reactive force equal in magnitude and opposite in direction by object B back on object A. And so equal and opposite forces rule, right? Now, guys, this is Newton's law that a lot of students can say the words, but then once I start prodding with application questions, it trips up a bunch of students. So let's see how you guys do. First of all, do you guys see that there's definitely a force interaction between two separate objects? So we need an object A and an object B. If I'm only focused on one object, within that object, Newton's third law doesn't really apply. I need two interacting objects. Let's take a look at this cannonball and this cannon. You guys see cannonball, cannon? Okay. So there's some gunpowder in here. There's an explosion. It pushes all different ways. Okay. And then the cannonball flies out really fast to the right. You guys see that? Now, guys, does the cannon itself recoil back to the left a little bit? Back to the left a little bit. Okay. All right. Now you guys tell me, guys, which force is bigger, the force on the cannonball or the force back on the cannon? Same. That's what equal is. It's the same force. There's some gunpowder explosion. It just pushes in all directions indiscriminately. It's the same force on the cannonball. It's back on the cannon. Wait, really? Is it really the same force? If it's really the same, why does the cannonball take off really fast and the cannon itself recoil back really slow? Because the cannon has so much more what? Mass. Mass. That takes back to Newton's second law of motion. It's the same force on the cannonball and the cannon, but the cannon is so much mass, it's very tiny acceleration back. You see that? Right? How about this one? Right? How about the Earth and the Moon? Oh, guys, does the Earth pull on the Moon? Yeah, that's what keeps it in orbit, right? We'll talk about orbits in a few weeks. Right? The Earth pulls on the Moon, keeps it in orbit. Something to do with that. Right? Guys, does the Moon pull back on the Earth? Yeah. Okay, that's why we have tides, right? Tides is mostly caused by the Moon, right? Now, you guys tell me, guys, which force is bigger? The Earth pulling the Moon and the Moon pulling the Earth? What? Same. The same. It's equal. It's the same force. Same force. Right here. I got one more slide for Newton's third. Oh, whoops. I got out of order here. Here it is. Does anybody know a YouTube channel called Veritasium? You guys know? Right. So Veritasium, he does a lot of science stuff, some physics stuff going on. I stole this slide from one of his old videos back many years ago. Right? So he's explaining Newton's third law. So suppose you have a planet and a moon, for example. Now, this should be true. There's an equal and opposite gravitational force between the two, even though they're wildly different masses. Right? So he says, hey, let's break it down. Suppose it was like a 3-to-1 mass ratio. Let's just focus on one mass at a time to help this make intuitive sense. Suppose it was 1 kilogram versus 1 kilogram. Now, if those were floating around in space, does it definitely make intuitive sense that they would be equal and opposite forces between two 1 kilogram masses floating in space? That makes sense, right? So those two are definitely equal and opposite. Okay? Now, what if you just focus on this one and this one? Could that definitely be equal and opposite between that kilogram and that kilogram? Right? What if you just focus on this pair here, that kilogram and that kilogram? Is that definitely equal and opposite? Okay? Now let's just put the story all together. If you didn't see it before, do you see it now? There's 3 units of force to the right, and there's 3 units of force to the left. So it's always equal and opposite forces between two interacting objects. Okay, right, guys. All right. So here's some new stuff. Dynamics, variables, and units. Now, for the first few weeks of school, you guys saw, displacement was in meters, got velocity meters per second, acceleration meters per second squared, time is in seconds. I think those are the main ones, right? Okay. Now let's break out some new ones. All right, so m is a variable. Remember, m's used for lots of things, but as a variable, that's mass. And guys, in this class, what is mass measured in? And don't say grams, say what? Kilograms, right? Guys, kilogram is the base SI unit for mass, right? So 1 kilogram. It's the only base unit that has the prefix baked into it. You guys know kilo is 1,000 or something, right? So in this case, 1,000 grams, right? But it'll be important when we're building composite units like force, right? Force in Newton. Oh, I was gonna ask you guys. You guys would have said force is measured in newtons, right? Now, force, all of force is just a push or a pull. When you guys were using the spring scales, you were pulling. There's some tension force in the spring, right? And it quantifies that. It says how many newtons it is. How many newtons, right? Right. So 1 newton of force. Now let me look at next. We're going to take a peek at the next poster real fast. Right? You guys remember Newton's second law of motion? F equals ma. Force F measured in newtons equals mass times acceleration. That's kilograms times meters per second squared. Okay? One really nice thing about the metric system is how all the units and composite units are self-consistent like this. Right? So here, for example, you guys remember this 100 gram lab? Oh wait, is that right? Sorry, that's the wrong one. Okay, oops. This 100 gram lab mass, doesn't this weigh 1 Newton? Right? If I pick it up, it takes 1 Newton of force to lift this. Right? Earth pulling down this 1 Newton of force. There's 1 Newton right there. Right? Now, if I toss this off the edge of the cliff, it's going to free fall at like 10 meters per second squared. Okay. And if it's 100 grams, is that like 0.1 kilograms? Right? So 0.1 kilograms, 10 meters per second squared. Guys, what's 0.1 times 10? That brings back to 1 Newton. This is 1 Newton of weight. Or wait, maybe that's one. Here, let me do a little more obvious example. let's break out 1 kilogram. Here's 1 kilogram right here. It says 1 kilogram. Okay? Suppose I push on this with 1 Newton of net force. It's going to accelerate. Guess how much? 1 meter per second squared. Right? 1 times 1 is 1. You guys get that? Right. Okay. So, but here's what I want you guys to see is you guys see how like kilogram is an ingredient that's baked into the cake of 1 Newton. You guys see that? Okay. So, all right. Moving on. If I ever write m times g in this class, that's 2 variables multiplied together. That's mass times gravity field, and I'm referring to the weight of something, which is also a type of force, so it's still quantified in newtons. Okay? Now, careful, if you pull a bottle out of your medicine cabinet, you see mg, they're probably referring to milligrams as a unit. Okay? But almost all the time in this class, I'm referring to mass times gravity field as weight. Okay? Okay, guys good? Okay. Next one. Let's talk about other kind of force. So suppose I break up here's a 1 Newton weight again. So 1 Newton weight. Okay. Now, if I throw this off the edge of a cliff, it would have a 1 Newton net force on it because it'd be in free fall. But if I just set it right there, now it's at rest. Guys, anything at rest has what is the net force on it? 0. 0 net force. Well, hold on a minute. This has a 1 Newton force pulling down. If it has 0 net force, do you think there's some balancing force holding it up? Hey, if I set it on a table surface, do you think the table surface is holding it up? Okay, that's what this is here. It's called the normal force. And I'll tell you where that word comes from. Do you guys know in mathematics, in a math class, if if 2 lines are normal to each other, that means they're what? Perpendicular. Perpendicular. That's what normal means. It means perpendicular. Okay, so if you have a flat horizontal surface and it's holding this up, isn't that upward force perpendicular to the surface? All right, that's what the normal force is. Later on, we'll get to inclines. If you have an incline, then that normal force is always perpendicular to that surface. Okay. F sub FR, force due to friction. So if I'm like dragging this across the surface, I bet there's some resistive force to that, and that's called the friction force. But it turns out there's 2 kinds of friction. There's static friction and kinetic friction. So if you push on something and it hasn't broken the initial friction yet, you're in a static case. If you break that initial friction and then you keep applying force to keep it in motion, that's kinetic friction. Turns out it actually takes more force to break the initial friction than it does. Like once you get it going, you don't need as much force to keep it going. Right? I'm trying to distinguish between these 2 static versus kinetic friction. Now, do you guys see this Greek letter mu? Now that refers to coefficient of friction. You guys have seen this a little bit the last couple of days. Let me remind you guys from one of your mini labs. You guys remember this one where you were lifting an object and then dragging it across the surface? Right, now I'm going to do some make-believe numbers here, but these are somewhat realistic. Right? Suppose you lift something and it takes 10 newtons to lift it, and you drag it across the surface, it takes 2 newtons to drag it. You see that? Right? You guys see a ratio here of like 2 to 10? Right? What if you pick a different object? Let's say it's the same materials though, and you lift it and it takes 5 newtons to lift it, and it takes 1 newton to drag it. You guys see it's the exact same ratio, 1 to 5, that's 2 to 10. That ratio has a name. It's called the coefficient of friction. So in this case, I can call it 0.2 or like 0.20. Is that right? Like I said. Okay. Now, if you change out the materials, put this on sandpaper, I bet that ratio changes. So this is like a material property, right? And then again, if you have not broken the initial friction yet, it's a static case. If you do break the friction and it starts sliding, that's a kinetic case. So this could be 2 slightly different numbers. It was like 0.3 versus 0.2. Static versus kinetic. Maybe it's like 0.5 versus 0.4. I'm just making up some numbers. Okay? But the static number is always more than the kinetic number. Okay? That's called coefficient of friction. And guys, if it's a ratio, guys, newtons over newtons, does that cancel? That's why I'm calling this unitless. See where I say it's a unitless ratio? Well, technically it's Newton per Newton. Is that all right? Right? I think if I'm keeping track right, I think this is the first time in this class I've ever written a number with no unit attached to it. Is it true? Like all the quantities you've seen so far, it's like some number of meters, some number of meter per second squared, some number of seconds, some number of kilograms, some number of newtons. Right? This is the first time I think you guys have ever seen a naked number in this class. Is other than just the algebra examples, right? This is a physical quantity with you don't have to write a unit with it, right? That rarely ever happens in this class, but that's one of the times it does. Right? Oh, we got here. Oh, how about a tension force? So you guys know tension force. Like if you pull with the spring scales, there's some tension in the spring. So I usually use F sub T, like force due to tension force. Okay. Sometimes you see capital T, but I try to reserve that for time period. Right? But tension force can still be in newtons because it's still a type of force. Right? Last one on this list, spring constant K, you'll see. So that's how stiff is the spring. And that's a ratio. That's a ratio of how much force do I need to pull it compared to how much does it stretch as a result, right? Isn't that how many newtons compared to how many meters? Hey, that's how you quantify newtons per meter. Here's a possible lab I might do with you guys one day. Right? Is what if I throw a bunch of spring scales at you guys? And I say, how stiff is that spring? How stiff is that spring? How stiff is that spring? And so you start pulling on it and you measure with a ruler. How much does it stretch? Right. And you take that ratio. Could you quantify how stiff is each one of these springs? No, it'll be different. Could you quantify how stiff they are? And that you could have a number, and that number will have a unit attached, and that unit is going to be how many Newton per meter. Right? You guys good? Good so far? Right. I have one more variable for you guys that didn't quite fit on this table because it's getting a pretty crowded table, and that's pressure. So I'll tell you guys what pressure is. Pressure is a ratio of force to area that force is acting on, right? And you can see that in the unit. So in this class, metric system, we're going to quantify pressure in pascals. Okay, so what is 1 Pascal? 1 Pascal is this. It's 1 Newton acting on 1 square meter. For example, does this lab weight right here weigh 1 Newton? One of your medium-sized lab weights. Okay, it weighs 1 Newton. Okay. Do you guys see some floor tiles? Can you guys count floor tiles? Let's count 3 by 3. Can you guys imagine a big old square that's 3 by 3? That's pretty close to a square meter. Pretty close, right? Imagine you had a big old foam board that was 1 square meter. I guess it would be a 1 meter stick by 1 meter stick. Got a big old square, 1 meter stick by 1 meter stick, big old foam board. And I stacked this on top of it, right on top of your 1 square meter foam board. That would be 1 Newton weight acting down on 1 square meter. That would be exactly 1 Pascal. Hey, you guys got that? Right? Hey, speaking of pressure, guys, are we inside an atmospheric pressure right now? Are we all feeling an atmospheric pressure? I guess we're all used to it, but we're definitely not in a vacuum. Right? In a vacuum, your saliva and your blood like boil away, and that would be no good. But okay, so we're in some atmospheric pressure right now. Right? Does anybody know how many pascals is equal to 1 atmosphere of pressure? We're down at sea level. That's 1 atmosphere of pressure. That's one way to quantify it. How many pascals is that? Take a guess. More. Keep going. More. Huh? More. Keep going up. More. Keep going up. Huh? Bigger number. Right. So what was the biggest number I heard so far? 47 pascals. More. Keep going higher. It's bigger than that. 100 more. 1,000 more. Well, not that big. All right. How about 101,000? 101,000. Guys, here's 1 Pascal is 1 Newton sitting on a 1 square meter foam board. If you had 101,000 of those, that's what we're sitting in right now, atmosphere. Right? Can you guys think of a different way to quantify pressure? You guys ever pump up your bike tires? How do you quantify how pressurized are your bike tires? Pounds per square inch, PSI, pounds per square inch. Could that be like force per unit area? It's the same concept, right? It's just American units. Right? How many pounds per square inch is the atmosphere on us right now? It's about 14.7. Guys, how heavy is a heavy bowling ball? It's about 14 or 15 pounds. Heavy bowling ball, about 14, 15 pounds, right? And 1 square inch, is that like this square, the little square right here? Right? Put it all together. Guys, what this means is you have a bowling ball of force on every square inch of your skin right now worth of pressure, which is a lot of pressure. Hey, I wonder if that has anything to do with this Greek mystery cup. I wonder, would this work in the vacuum of space? I wonder if you need an atmospheric pressure to make this work at all. And if you do, what's the limiting factor? We have a limiting pressure, right? I wonder how big you can make that thing. Just throwing some questions out there for you guys. All right, let's do some motion. All right, so at this point in the class, you guys remember have 2 perspectives on what is acceleration. The first perspective is kinematic. It's a rate change of velocity. You guys remember those 3 kinematic equations? All I did was rearrange them and solve for A. Now we're getting a new perspective on acceleration, which is Newton's second law of motion. You're saying, where does it come from? It comes from a force acting on a mass, right? Now you can bridge this together. So for example, suppose I say you kick a soccer ball with some force. So now I know my kicking force, suppose I give you some number of newtons. And you know the mass of a soccer ball is so many kilograms, right? And I say that kick lasts for like a fraction of a second. I tell you, maybe it's like 0.4 seconds or something. Your foot's in contact with the ball. I say, if the ball started at rest, how fast does the ball leave your foot? Right? Now I'm mixing and matching dynamics and kinematics, but now you can bridge it together with acceleration. I know the force divided by mass of soccer ball. I know how much the ball was accelerating while I was kicking it. I know how much time that lasted for, and the ball started at rest. I can use this one right here to figure out how fast it was leaving my foot. You see that? Big picture, right? The bottom half of this is turntable physics, like rotation. We're not there yet, but just in a straight line. Okay. All right. Okay. Here's the last poster today, and then we're going to kick over to PowerPoint after this. Free body diagram. Free body diagram. All you're doing is you create a diagram showing all the forces, and a few months from now we'll do torques or moments acting on an object. But for now, you just care about forces acting on an object. I gave you guys some examples here. Here, for example, if something's in free fall, go to the edge of a cliff and drop a ball off the edge of a cliff. Okay. Is a weight pulling it down? Yep. Right. Guys, speaking of which, if that's the only force on the object, if there's no air drag, only the weight's pulling down, right? Is that would be the net force? Right. Let's do Newton's second law of motion. You guys remember Newton's second law of motion? If I Newton's second law of motion. Okay. Guys, if the net force is mg, let's put in mg right here. And the mass of the object is probably just m. Hey, does the m cancel? And the acceleration of the object then is equal to g. Okay. That's why, you guys remember Galileo experiment? Galileo threw this off a cliff and this off a cliff. And remember they hit the ground at the same time? Right? They fell together. Now they were both accelerating. They were both accelerating the same. They were both accelerating at the rate of g. Because it doesn't matter how much mass is. Right? You've got different weights, different masses. The ratio is just free fall gravity. Right? We're going to eventually do inclines. You might have like 3 forces on an incline, possibly. Okay? I bet you guys did something similar to this the other day. You drag a block across the surface. You might have the weight, the normal force, an applied force, a friction force. You might have all that going on. Okay? Because some of these might be in motion. There might be a velocity involved. Right? Guys, did I draw any velocity vectors here? Did you see any velocity vectors? No, because these are all force vectors. Do you guys think, I haven't written your next quiz yet, but when I do you think I'm going to have you draw some free body diagrams, right? And do I only want you to draw force vectors on those free body diagrams? Yep. Are velocity vectors force vectors? Yep, it's a different concept. Okay, so careful about that. That's a common, okay. All right, let's flip over to, wait, adjust my camera a little bit. Set. Free body diagram. It's not too bad, it's all right. All right, we're gonna kick over to a PowerPoint. Right, you guys got your notebooks out. All right, we're doing free body diagram PowerPoint. By the way, do you think I put this PowerPoint you're about to see on Google Classroom? Think it's been there the whole time? Right, so if I accidentally go a little bit too fast, you can always go back and check. So free body diagram, let's start with definition type. Diagram showing, okay, just the forces acting on an object, and a few months from now, might bring in a torque or moments, but for now, just the forces, right? So draw force vectors to represent the relative magnitude and direction of the forces. So suppose there's multiple forces on an object, and can you represent forces with these vector arrows, right? What if I draw 2 vector arrows, and one's really long and one's really short? Does that imply a really big force and a really small force, right? So the length of the arrow is going to be proportional to the force. The length of the arrow is directly proportional to the force. If it's twice the length, that means twice the pushing force. Okay. This next line, I'm saying for AP because AP is really strict about this next rule, but really this is true for all my classes anyway. Okay? Always connect the tails of the vectors to the center of mass dot. You see a black center mass dot right there? You see the tail of this vector? Okay? And draw the force vector extending away from that center mass dot. Right? So that's a common thing you'll see throughout this entire presentation. I'm connecting the center mass dot to the tail of the vector, right? And draw the vector going away. Also, I've labeled this vector. I labeled this one mg. Could that be with the weight of the object, right? Remember, forces are measured in newtons. velocity vectors, meters per second, are not force vectors. Acceleration vectors, meters per second squared, are also not force vectors, although accelerations are caused by forces, but it's a different concept. Okay, that's good. All right. Let's look at this one that I drew on the right side here. Suppose you just saw that out of context. That's all you get, that one force vector, boom. Right? What can you say about that object as it's drawn right there? It's in what type of motion? Free fall, exactly, free fall. So maybe you went to the edge of a cliff and you dropped this off the edge of a cliff. That could be that. Right? What about this? Because what if you throw the object straight up in the air? Now, while you're throwing it, there's a force from your hand, but let's say after that, after the object leaves your hand and is moving up, slowing to a stop, is that also the free body diagram for that situation? Yes, it is. Notice there's no velocity drawn, but the velocity could be any direction. It doesn't matter. Guys, could you go to, hey, how about, do you guys remember taking those projectile cannons and blasting little bouncy balls off this balcony here, right? Well, let's say after the ball has left the spring and it's in motion, does it follow a parabola path? Okay. And the entire time it's following, is that right there? Is that the free body diagram of that bouncy ball the entire time it's on the projectile? It sure is. That's it. That's it. Right. Notice it's ambiguous as to the direction of the velocity, right? You don't know. All you know is the force, and there's only one force in free fall. That's the weight. Okay. Right. Let's amend this a little bit. Here's a new force. Bam. Guys, if I introduce a normal force, now have I just put this in object in equilibrium? Right. So it's probably at rest. Right. Maybe I just set it on the table. Could that just be an object sitting at rest on a table? Right. There's an object sitting at rest on a table. Right. I'll tell you what else it could also be. Maybe this object is in an elevator and the elevator is moving at constant velocity. Is that, if you were inside that elevator, wouldn't that be indistinguishable from being at rest? Constant velocity, right? Is that true? That could also be that, right? Right. Here, one more detail. Now this gets a little bit more nuanced, but make this point while you guys are looking at this. Right? Do you guys remember Newton's third law of motion? For every force, there's an equal and opposite reactive force. You guys remember that? Right? Now, careful with your free body diagram, because your free body diagram, aren't we just focused pretty much on one object at a time? But Newton's third law, and I have the poster hanging right over there if you want to reference that, doesn't it talk about an object A and also an object B? Okay, right. So let's go back to this diagram of maybe this object is just sitting at rest on a table. Right. Okay, I see two forces that they look equal and opposite. Right, guys, are these two forces equal and opposite because of Newton's third law or because of equilibrium? And only one of those is correct. Which one's correct? Equilibrium. Okay, because this is not a Newton's third law pair. Let me talk about what the Newton's third law pair actually is, because there is a Newton's third law pair, right? But it's not these two forces, right? Right. So, do you guys see mg? This is the Earth pulling down on the block, right? Guys, if the Earth pulls down on the block, what is the equal and opposite force always to the Earth pulling down on the block? And is not the normal force. What's the equal and opposite to Earth pulling down on the block? Is what? How about this? Right, guys, everybody's sitting in a desk right now, right? Sitting in a chair, right? Is the Earth pulling down on you? Right. So okay, so you have a weight. The Earth's pulling down on you. What is the equal and opposite force to the Earth pulling down on you? Are you also pulling up on the entire Earth? Is that true? Is that true? But which force is bigger? The Earth pulling you down, or are you pulling the Earth up? Huh? For every force, there's an equal. It's the same. That's the Newton's third law pair. Okay, that's a little nuanced question. That's the equal and opposite force, right? Right. Let's do the other one. You guys see this normal force here? We're back to this PowerPoint. You guys see this normal force right here, right? The equal and opposite force to the floor pushing up on the block is actually the block pushing down on the floor, which in this case happens to be equal to its weight, but that's not universally true. What if this was in an elevator? What if the elevator is accelerating upward? In that case, do you think these two forces would be different? Yeah. So in that case, the normal force would be more than the weight. So these two could be mismatched, but you need a second object, an object B, to have a Newton's third law equal and opposite pair force. Okay, is that right? That's a little bit more nuanced. Right. Okay, so back to here. All right, block at rest on a table. Well, we basically just did this one. It's got a weight down and a normal force up. Okay, could that be a block at rest on a table? Okay, boom, boom. Right, we're just focused on the block itself. Right. Now for these next slides, can you guys write a scenario in your notes and then draw the free body diagram? If you guys can draw these before I reveal the answer, that's a good indication you know how to solve these. Right? Today, they're mostly pretty straightforward, and then the more exciting, fun ones we're gonna have to save for another day, but we'll get as far as we can today. All right, block at rest on a table. Let's say you're pushing it horizontally, but not with enough force to overcome the, let's call it static friction between the block and the table surface, right? So the block's still at rest, right? You're pushing on that block, but it's still like stuck. It's not actually moving. Okay? Go ahead, in your notes, and if you need paper, I got some paper on these stools. But if you got a notebook, that's a good place to write this free body diagram. See if you guys can get these free body diagrams before I reveal the answer on the PowerPoint. I guys got some paper. Everybody got some paper here to make sure. It's got. All right, you guys got some paper, some notes. Okay, go ahead and jot down the scenario real fast. Then draw what do you think the free body diagram looks like for that scenario. But yeah, we're going to start with some that are pretty fundamental today, and then the more exciting ones we'll have to save for another day. We've got so much class time. All right. So here, let's start revealing this. At rest on a table, do you think you probably need a gravitational force? Right. Otherwise, you're just floating around in space and probably nothing else shows up. Right. So let's do that. This block's got to wait. Right. But hang on a minute. If I stopped there, it would be in free fall. So if it's supposed to be something to rest on a table, there must also be a what force on it? Starts with an N. Normal. Okay. And that goes straight up. Right. And that's going to balance out the weight. Right. Not because of Newton's third law, but because of equilibrium. Okay. So the block is not accelerating up or down. Okay. Right. Now, suppose you push this block in one direction. Hey, could that be like an applied force pushing it? But if the block is not moving, guys, if the block is anything at rest, what do you know about the net force? Have to be zero, right? So all the forces have to zero out. All right. So here's the last two. Maybe have an applied force like F sub push, applied force. But do you guys see how the friction is opposing that intended motion? Is that right? And friction force will always do that. Friction force will always oppose either the motion or the intended motion of an object to try to slow it down, keep it from moving. Right? Something like that. All right. Sometimes, like when we get to the block being in motion, well, I think it's the next slide we're about to do. Okay. All right, so you guys ready for their next slide? Almost. All right, so see you guys wrapping up the notes here. Right. So here, I got 4 forces that all balance out. Vertically, they balance out. There's 0 net force vertically. I got 2 horizontal forces that also zero out horizontally. So there's 0 net force, which 0 net force is one of 2 things. It's either at rest or it's constant velocity, but it's definitely 0 acceleration. Okay. Something like that. Okay. And notice I labeled all those forces. Got weight, got normal force, got the applied force, we got the friction force. Boom, 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 boom. So got. All right, next slide. Let's have a block on a table. Let's push it horizontally, just like before. But now the block is going to move with constant velocity across the surface. Okay. Now I did throw in a fat green arrow to indicate velocity. Guys, is this velocity arrow part of the free body diagram? No, right? So if I ask a quiz question and I have something in motion, I might myself print a big fat arrow just for context, right? Because that could help you figure out something about the forces. But for the free body diagram, I really care about you're drawing the forces, right? And velocity vector, of course, is not a force vector. So go ahead. Right. So now you're pushing that, what do we call it? A block. You're pushing that block across the surface, and it's moving with constant velocity. So take a trip around the room here. See how many guys are getting this. It's you're pushing a block, and it's moving with constant velocity. What does that mean in terms of those force vectors? What do the force vectors look like for constant velocity? Here, give you guys a little hint. Guys, constant velocity. Anything with constant velocity, what is the acceleration equal to? 0, because it's not speeding up or slowing down. That's what constant velocity is. Hold on a minute. If there's 0 acceleration, what do you know about the net force? Is that also 0? Right? Kind of like Newton's second law of motion. 0 net force, 0 acceleration. Huh. You guys think that all the forces are also gonna cancel out with this one? Here, I'll give you guys the answer. This block has a weight pulling straight down. You guys got mg. Do you guys think the normal force from the table is holding it up? It's a flat horizontal table, probably, right? Do you guys think if it's moving to the right at constant velocity, I'm probably pushing it to the right to keep it that way? Right? Now, guys, if I stop right there, is that constant velocity? No, because there's a net force. That might be like maybe like an air hockey puck that you're pushing. So that would be speeding up. Guys, I need one more force. What's the one more force I need? Friction force. Okay. All right. And that zeroes out all the forces, doesn't it? Wait a minute, zeroes out all the forces? Guys, is that slide right there identical to the previous PowerPoint slide? It sure is. If all you had was that free body diagram, suppose this page comes out of a book and I don't know, maybe got water damage and it ruins the, you don't know what is the scenario. All you have is the free body diagram forces, right? And that's all you have. Could you distinguish between if that block was at rest or constant velocity? Could you tell the difference? No, it would be ambiguous. Sometimes these work out that way. Because what if you're a ladybug that and you just land on that block right there? And let's say you close your ladybug eyes. Can you distinguish the difference between moving constant velocity or being at rest? No, you can't tell the difference. It would be indistinguishable. And that shows up in the free body diagram. Right? Now, here's maybe how you could tell possibly. If I told you if it was static versus kinetic friction. If I told you that, you say, okay, well, static, it's definitely at rest. Kinetic, it's definitely in motion. Okay. Right, but, all right, you guys ready for the next one? Let's do block on a table, push horizontally so that there is a net force. There is a net force. And guys, if there is a net force, is the block accelerating? Yes. Yeah. So anytime there's a net force, there has to be an acceleration. That's Newton's second law of motion, isn't it? F equals ma. Right. Well, a net force is going to result in acceleration. A equals F over m. It's a little better. All right, here, I'll start to rebuild these. Do you think this block has the weight that's had all along? If it's on a table, do you think there's also a surface force from the table holding it up called the normal force? Right. Now, if there is a net force, I bet this is one possible solution. That might not even be the only solution, but maybe I'm pushing more than the friction is. So maybe the block is speeding up to the right. Okay. Let me show you guys another one. I'm just going to point this out in class. But we'll eventually do this too. You guys, if you're sitting in class, you guys see a car braking to a stop right here, right? Could that also kind of be that? Or what would you do this? What if you gave the block a push and then you just let it go and it slides to a stop, right? That could also have a net force, right? It'd be slowing down. Only 3 forces. All right. Let's try guys, rock and free fall. No air resistance. So go ahead, drop that down real fast in your notes. Say rock and free fall. No air drag. Okay. This could be one of several scenarios. You could go to the edge of a cliff and drop a rock. You could throw the rock down, and this free body diagram is after it's left your hand, so it's already in motion. Right? You could throw the rock straight up. You could throw the rock to the side. Right? Now, any of these scenarios is after the rock has left your hand, whether you drop it or throw it in any crazy direction or any speed, it's all the same answer after it's left your hand. Do you guys have the answer in your notes by now? Right, boom, that's it. That's the whole story. Done. Right, you guys got that? Right, done. Right. That one free body diagram describes all those different scenarios. Can you guys look at that? Guys, do you guys know which direction this rock is moving? No, it might be moving down, it might be moving up. It might be moving to the side. It might be moving at a 40-degree angle. You don't know. All you know is it's accelerating down. It's in free fall. Right. Here, I'm going to skip a couple because I got a parachutist later on that's really similar to those. So save those for later. Right. A boat moving through water at constant velocity. Right, go ahead. Draw a boat, and in your notes, write boat constant velocity. Right. Again, I gave you guys a kind of a fat green velocity vector, but that's not part of the diagram technically. Right? But it might give you guys some helpful context. Right? Now, most of the time in this class, we ignore drag forces, right? But it's usually like air drag. It's kind of fun. Hey, do you guys think that water? Do you guys think that boats in water? Do you think water is about 1,000 times as dense as air? And if that's true, do you think the water drag force is pretty significant enough. It's probably hard to ignore, right? I bet there's going to be a water drag force as one of the forces, I'm thinking, right? And yet, constant velocity, guys, what do you know? Constant velocity tells you about the net force. What is the net force on that boat? 0. It has to zero out for anything. Constant velocity is an example of equilibrium. Now let's start going through the answer. Guys, do you think the boat's being pulled down with a gravitational force, like its weight? Let's throw weight on there. We're trying to sink the boat, right? That's trying to sink the boat. Guys, what's keeping the boat afloat? What's it called? What force keeps something afloat? Buoyant force. Buoyant force. Okay, so there's the two vertical forces, right? So we got the weight down, we got the buoyant force up, keeping it afloat. Right. Now, if you gave that boat a push and let it go, I bet the drag force would slow it to a stop pretty fast, probably. Right. So to keep it going at constant velocity, do you think maybe the propellers and the water have to push against each other? You guys think? Right. So here, guys, here's the last two. I got an applied force. This is the water pushing against the propellers. And I got a drag force. That's the front of the boat dragging against the water. But you guys see how everything is balanced? And you know they're balanced because constant velocity is an example of equilibrium. You guys got that too? Great. While you guys are finishing, write that down. Let me remind you guys something about Newton's third law, because I see a bunch of stuff canceling, but it's only canceling because of equilibrium. Okay. Guys, what is, let's go through these one by one. Guys, what is Newton's third law to the Earth pulling down on the boat? What's the equal and opposite to that? How about, does the boat pull up on the entire Earth? It does. Right. What's the equal and opposite to the water pushing up on the boat? Buoyant force. Does the boat push down on the water? Yep, right. And that's not necessarily equal to, although in this case it happens to be equal to its weight, but that's not universally true. What if you push the boat down into the water and let it go? Boing, boings up. I bet these forces could be different if you did something like that. How about here's the water pushing against the propellers. Do you guys think the propellers are pushing back against the water, right? And here's the water on the front of the boat dragging the boat back. Do you think the front of the boat is also pushing the water forward? Okay, so there's third law for each one of those individually, but you need some other object like the Earth or the water or something. All right. Can you guys draw 3 forces to put an object in equilibrium? Now, there's many solutions here, so I'm going to show you guys at least 2 on this PowerPoint. I'm going to take a trip around the room. This one takes a little creativity. Some students get this. Not everybody gets this, though. I wonder how many students today, right now, are going to get this. Can you put 3 forces in equilibrium? How can you do that? 3 forces in equilibrium. Who's going to get 3 forces in equilibrium? Who can figure this one out? Guys, equilibrium, does that mean all the forces zero out? They all zero out? How can you do that with 3 forces? You zero out. Can you zero something out with 3 forces? How can you do that? I guess with all these, I'd ideally like to give you guys more time, but great. Let me move things on along a little bit here. So we switch over. 3 forces in equilibrium. How could you possibly do that? Hang on a minute. I think you guys did that 2 days ago. Guys, is that right there? Is that 1, 2, 3 forces in equilibrium? That could be it. That could be it right there. Right? So let's flip back over to this PowerPoint. I just wanted to point out that you guys did do that the other day. All right, so you could have, hey, could you guys have 3 guys playing a 3-way tug of war? We got 3 ropes tied together, that pulling all different ways. Right? So this is one possible solution. Guys, suppose this is 3 guys playing a 3-way tug of war. Is this guy pulling left as much as this guy's pulling to the right? Yep, I'm thinking in terms like Cartesian coordinates. Suppose you introduce like an x-axis and a y-axis. Yeah, this guy's pulling left as much as this guy's pulling right. Is this guy pulling up as much as these 2 guys are collectively pulling down? Yep, this is down a little bit. This is down a little bit. This is up a lot. Maybe, right. Let's do another solution. What if you had something like that? Like pull it up a lot and pull it down a little bit, This could be 10 newtons up and 5 and 5 down. That could also be 3 forces in equilibrium. Good to do, right? So there's many solutions. There's 2, right? Parachuter. I'll say you go make a running jump off a cliff. I'm glad I brought my parachute. You open your parachute. You're flying down. Now, guys, that parachute, this is going to work from the principle of drag force. You definitely need an atmosphere to make the parachute work. Go ahead, draw the forces acting on the parachute is No, I said before terminal velocity. Right. Do you guys think the faster you're falling, faster, is going to build up more and more drag force? Right. Here, I'll point this one out in class too, and then one day if you're watching the video, probably break out the poster for the video. Okay. I have a poster in class that says drag force with a parachute. Do you guys see drag force is proportional to v squared? Okay, that means if you're going 3 times as fast, you build up 9 times the drag force. Okay, but maybe the important takeaway is the faster you're moving, the more is the drag force. So, no, when you say first open the chute or right before you open the chute, maybe you just got this going on. This guy has a weight, right? mg, right? And let's say you're not falling very fast yet because you just jumped off the cliff ledge. Right? So maybe it's a little tiny force. But the faster you're falling, do you guys think that force is building up more and more? Right? So that drag force builds up more and more. Now, if I stop right there, that could be the answer to that one. Okay. Guys, is there still a net force on that parachutist? Is there still a net force? Yes, there is. So is he still continuing to accelerate faster? Yes, he is. Is he accelerating at the full free fall rate anymore? No. So if he's like 100 pounds here and this is like 50 pounds, you have to subtract the two. Well, I should use newtons, but you guys get the idea. You take the difference for the net force, you divide by his mass, and you're going to get less than 10 meters per second squared. Maybe you get like 5 meters per second squared, but he's still speeding up. Okay. Now, the process will continue until next slide. Let's do something called, I should have asked you guys, I guess about terminal velocity. Guys, terminal velocity. Do you think that at some point he's going to speed up until that drag force builds up to the point that it matches his weight? And then, guys, once the drag force matches his weight, is he in equilibrium at that point? Does he have 0 net force? Yes, he has 0 net force. He's equilibrium, which means his acceleration is equal to what? 0. Now, what does that mean? Does that mean bing, just hangs at rest in midair? Is that what that means? Is 0 acceleration 0 velocity? No, those are different ideas. Because 0 acceleration means that however fast he's moving, he's just going to keep going at that velocity. He's just not going to change his velocity anymore, right? And that's called, guys, that's what terminal velocity is. You guys have probably heard that term, terminal velocity, right? Guys, do you need an atmosphere to reach terminal velocity? Yeah. Like if you fill in a vacuum, guys, would a parachute even work in a vacuum? No, you just plummet. Right. One more, guys. Here's the last one today. Let's go to deep space. Let's say you got a rocket screaming through deep space at 10,000 meters per second. It's going. There's no significant gravitational forces nearby. It's just screaming, constant velocity, deep space. Sure. Guys, what forces are acting on that rocket? None. You got it. It's just coasting from inertia, isn't it? Right? How would you feel inside that rocket? Would you just be floating around like an astronaut? Yep, you'd be floating around, right? Kind of like International Space Station. You see you floating around, so they're whizzing around the Earth once every 90 minutes. Right? How about what if you did turn off on the rocket boosters? Now there would be a net force, and now the rocket would be accelerating, which would no longer be constant velocity. Okay. So you guys got that? Oh, could that be like Voyager spacecraft? That could be Voyager spacecraft, couldn't it? It's just going from inertia, right? It doesn't need a net force. It doesn't need any force. It's just going. Yeah. All right, and that is our pause point today. Oh yeah.